Hello, hello, hello. Good afternoon, Internet. Welcome back to the same math time and the same math channel. We are again for another week. Uh, yeah, we're starting in. This is week 11. Week 11 of distance teaching. Boy, oh boy. Really, yeah, it's hard to believe. It's hard to believe it's gone on this long, hasn't it? But it is stream 49, right? Because we had 2 days missed due to holidays, which means so we get to talk about having 7 square meals a day. Boy. Now, that is a little bit of a pun, right? A little bit of a pun on what my background is here, because any townies should know what part of the city that is, right? People from St. John's. I mean, this is the from St. John's. Now, this is the scenic part, right? This is really good stuff. This part of the city here is, of course, where? It's the gut. It's the gut, right? That's what it's called. It's the gut down in Kitty Vitty, right? So yeah, 7 square meals a day fills the gut up nice and good, right? Yeah. I mean that's a boy, it's a bit of a stretch, for that pun. Um, yeah, this is of course one of the nicest views of the city. This is from strangely enough now, as you see down below, I'm looking right above these buildings, and those buildings that I'm right above in this picture are some of the ones that you more commonly see in the pictures of the gut, because this is sort of the definitely the least common angle, right? Because those buildings are quite difficult to get to. Actually, some of them you kind of had to get to via boat. I'm up a little bit above them, as we see down in the bottom left there, right? You can see the roof of one, because I'm taking Sugarloaf Path. Yes, hello, Esther. Yes, thanks for dropping in there. It does take a few seconds for me to respond because of sort of delays in the internet and things, right? Normally, by the time I see your message and respond to it, it's probably, and more importantly, by the time that you see the video of me responding, it's a solid 30 seconds at least. Uh, yes, this is from Sugarloaf Path, which is one of my favorite trails around the city, and it's sort of had to go down a ways as you see on the cliff there to the right, sort of above my head, right? It's a very nice view of the city though. Sugarloaf Pass, very. I mentioned it on a few streams ago. Very scenic area. We can also see, yes, this is sort of like if we look right here where I am now, right? If I come back up across the cliff and then sort of turn to my left, then well, and walk away, so walk a solid, 300 or 400 feet. You'll be treated to vistas like this one, right? This is pretty nice. This is looking out to the left there. That is the Atlantic Ocean, the wide swaths of the Atlantic stretching across. And we do see in the left, of course, the sort of middle left, there's that's still more of the Avalon Peninsula. I would have to turn a bit further left, further that way, right? Stage left, a bit further stage left to be actually looking across the Atlantic. But if I was to turn to my left here in this picture, like the next piece of land would be like France, right? Boy, it's that's a ways. It's a ways to go. Today, before I get started, I don't have as much banter as normal. I do want to just talk through a little bit about what's going to happen for the transfers. Uh, um, this is a bit more technical stuff. I did just want to say it sort of aloud in words so that people can understand it, because I know sometimes it's difficult to maybe understand everything from an email, from reading it, I guess. But CBS campus will close on June 26th. I mean, as of June 26th, 2020, as of the end of this month, basically, um, Jennifer and I won't be teaching your online courses anymore for any of my students, of course. So someone like Slayer Darth who just hangs out in the chat, maybe. I mean, not just. I mean, hanging out. I shouldn't say just, right? Hanging out in the chat is the best thing you could possibly do. But what I'm saying is, for any of my students that are enrolled at the Academy Canada class, I won't be teaching your online courses anymore as of June 26th. So I believe if I'm counting correctly, we're going to go up to math tutoring day 63, and I'm going to miss day 64. I'm going to miss day 64 by one stream, which is heartbreaking, right? Because 64 is a great number. It's a square number. It's a Nintendo, right? It's loads of stuff. It's one of the best numbers. Um, maybe I'll do one fun stream and like the last Friday in the evening or something, just to take it, knock that one up to day 64. Maybe we'll see. But either way, as of June 26th, I won't be teaching the ABE program at Academy Canada until, again, I guess, in September. And we don't know whether September is going to be online or on site at this point, but I will let the students know as soon as I know. But you may be told that by the teachers at Kenmount. It's entirely possible that we won't know by the end of June, right? But yes, the stream will also end at the end of June, right? I won't be carrying on streaming just for something to do. I mean, plenty of people do. I mean, Twitch is full of those people, right? But if I was to stream for something to do, it wouldn't be math, right? It would be one of several video games, and perhaps I will do that, maybe for something to do. But I won't be doing the math stream like that. Your teachers at Kenmount, if you transfer, will have their own sort of online setup. I believe they use Skype for Business, but that'll be up to them to tell you which ones they use and don't use. Any courses in progress, they will probably just pick up and keep running with. I can't say for sure, but I imagine they will. They use most of the same materials that we do. For English courses, it might be different, right? It's entirely possible that they'll want to use different English textbooks than what we use in CBS. So, especially if you're doing an English course, make sure to bounce it off your new instructor, what you're currently doing, to see if they'll be able to keep you going on those. Right, but for your guys' perspective, there won't be a ton of difference, right? It'll just be when you come back in July, right after Canada Day holiday, then it'll just be someone different teaching your course, and there'll be a different setup. Um, yeah, I don't know what they're going to do for testing or for submitting work or whatever like that, but I gather they will have to tell you, I guess, right? But either way, like I mentioned, email Judy and any of my students. Of course, you have that email address already. I'm not going to put it out over the stream, right? But you've got that email address sent to you today. So if you do want to transfer to Kenmount to continue through July and through part of August, um, then let Judy know, and she'll take care of transferring you. There should be no problem about space at Kenmount. Um, yeah. Just tuning in, any update on September? Probably online for the rest of 2020, eh? Well, I mean, I don't know. I honestly, I haven't been told. I know Munn is going with an online model until January 2021. Excuse me, boy, hiccups. I haven't been told for sure what Academy Canada is doing. I mean, I think smart money is on it probably being still online, but you know that I guess that depends on how the Newfoundland government ratchets back the COVID-19 response between now and September, maybe. I do think that we might not know. We might not know before Jennifer and I are done on the end of June. So you might be being told that by the teachers at Kenmount, right? Or if you're not transferring, um, just periodically check the Academy Canada website, and they hopefully should have some details up there whenever they're released, right, about how September is going to shake out. But yes, there won't be this stream. There won't be a stream afterwards. I mean, I don't know. Maybe Ken Mount Road's doing a stream. I don't believe they are. But they will have some sort of method. But anyway, this stream, NL Mathman, um, NL Mathman's done, over as of June 26th. Um, maybe I'll be back for season 2 in September. I don't know. We'll see. We'll see. How do we get our diploma when we graduate? Those are mailed out to you. Nor sometimes you can have them mailed to the site. You used to be able to, but now I guess you won't be doing that. So yes, those will be mailed to you in Canada Post. So when you graduate, yeah, you'll be able to contact. I believe those are sent from Corner Brook. I think that's where those are printed. But yeah, if you contact Judy or someone like that, they will be able to put you in contact with the right person to get those sent out to you. But those will be handled remotely, by mail. Anyway, it's just a little bit of housekeeping stuff to get started there. Maybe not quite as interesting as my normal banter, right? Because my normal banter is always like really interesting, like of course. Um, Over here now today, we've got a few topics that I'm going to get to. I'm going to do permutations of permutations and combinations. Talk about the definitions and the NPR formula. Now that one is for Calais, and I believe Calais is not able to make the streams due to work commitments. So I'm going to leave that one till last, actually, because if I'm, if I'm just sending her a video, then I can send it at any point. Um, radicals, word problems, and extraneous roots. Those are for Betty Ann for a little bit of review of an activity she did and practice for a test. And then geometric transformations. Esther, I see you're in chat there, so I'll start off with the geometric transformations ones. Betty Ann, if you are in chat as well, you can let me know. Let me know if there are any specific questions you want me to do. Otherwise, I'm just going to do those, basically the ones I indicated earlier that I was going to go over. Trying something a little bit different with my chroma key today. I think it looks better overall. I think the light level looks better, but occasionally I'm getting some of the blue in the background bleeding through. But no, I think we're doing pretty good, right? Except for when I move a piece of paper in front of the camera. But these things happen. So anyway, I'm going to start off with rotation. So let's go on over now to the working display. Here we go. So there's my piece of paper. Good. Right, what's up in the corner there is stuff for Calais. So let me change that over to being these ones. So now, Esther, this is the worksheet that I'm going to be doing. You notice I'm going to do numbers 1, 4, 5, and 6. I think you can probably leave out question 2. Question 2 is not really any harder. It does bring in reflecting a line across a diagonal line, and you haven't really done reflections across. Sorry, not rotation. Jeez, here I am messing it up. Question 2 involves reflecting over a diagonal line, and that's not really any harder. Just you haven't seen it yet. So I figure that we might as well just cut our losses and just leave out all the stuff that we absolutely don't have to do, right? So when you're doing this worksheet, you can skip question 2. It's really not that hard because it's just a diagonal line. Y equals negative x is just sort of a diagonal line from top left to bottom right, but reflecting in a diagonal, it's not really any more work. It's a tiny bit more work because you've got to do rise and run, right? Like a right angle triangle instead of just doing one direction. But either way, we'll stick with the ones that are like the ones you saw in your other activities where you only had to do one direction. I don't have any puns about One Direction, the band, to make there, simply because I am blissfully unaware of anything that One Direction has ever done, and perhaps will ever do. But anyway, too much of a music snob. Too much of a music. I'm not at all a music snob. I just knows what I likes, and the things that I likes tend to be not modern pop that kids listen to. Okay. Let's start off with. Let's do the question 5 first. Question 5 is easy peasy, right? So question 5 says translation of 5 left and 2 up, right? So we have to know the difference, right, between translation, reflection, and rotation. Translation is the easy one. Translation is just move. All you're doing is just taking a shape, and you're literally just sliding it. 5 left, 2 up. So kind of like that, right? I mean, obviously, the shape didn't move on the paper. I would have to use a computer if I was going to do that. But like you can just imagine it like this, right? That matches fairly decently. 5 left, we're just going to move it left. 2 up, going to move it 2 up. So it's going to look kind of like that when we're done. But we're not just going to eyeball it. We're going to pick each of the corners of the shape and move it according to this translation. So 5 units left. Well, we start here on this point, right? 1, 2, 3, 4, 5 left. 1, 2 up, right here. So there's that new point. Going to do the same thing for this one. 5 left. 1, 2, 3, 4, 5. 2 up. 1, 2. Same thing here. 5 left. 1, 2, 3, 4, 5. 2 up. 1, 2. Right here. There we go. And then we just take those 3 points that we've translated and we're going to join them up. Line here. Line here. And line here. There we go. So this now, shaded in a bit so it's easier to see. That is our new shape. 5 units left. 5 units left and 2 units up from where it was previously, he says with painful enunciation. Okay, so number 4. Number 4 is a reflection across a line y equals 1. Well, where's the line y equals 1? Well, we know a y equals line is always a horizontal line. And why is that? Well, because it's all the points on the graph that have a y coordinate of 1. right? Well, this point has a y coordinate of 1, so does this one, so does this one, so does this one, right? So y equals 1 is going to be the whole line on across there. So I'm going to first thing I'm going to do is I'm going to color in my reflection line, right? So this is that is the reflection line that I've drawn there in red now. So now I'm going to do all the points. Well, the points, remember, are just the same distance away from the line as they were before, just they're on the opposite side of the line, right? So for example, this point here is 1 up from the line, right? So the new point, once it reflects, is going to be 1 down from the line. It's going to be right there, right? So reflected points are equidistant from the reflection line, but on the opposite side. Equidistant meaning the same distance as the ones that were there before, right? So this point, like I said, this vertex here, this corner, was 1 up originally, so now is 1 down, right? So say this point here was 0 up, so now it's 0 down, right? A point that's on the line sort of stays put. This point here, this one up in the top, was originally 1, 2, 3, 4 up. So now it's going to be 1, 2, 3, 4 down. This other one was 4 up. So it's now going to also be 1, 2, 3, 4 down, like so. And now I just got to take my straight edge and join them up. Like so. Like so there. Like so there. And then like so. Now I'll color it in a little so the shape is a bit clearer. And there we have it. Right? So that is our reflected shape across the line y equals 1. It's just that easy, right? All we've got to do is draw new points that are the same distance from the reflection line that the original points were. Now, the ones that we have a little bit of work to do, as you've seen, right, are the rotations. Now, I understand rotations are way harder than the others because they're just so much more work, right? There's way, way, way more steps in rotations. But again, we'll show you how we walk through those individual steps. Now, I've blown mine way up, as we see over here, so I've got a bit more space to work. And please stop me if at any point what I'm doing doesn't seem to make any sense, or if you have any questions at all. Right? That's one of the benefits of a stream like this, as opposed to just a recorded video, is that I'm able to get feedback from you in real time, and you're able to engage with me kind of like we would in class, right? You're able to stop me partway through an example if you're finding something difficult, or if something doesn't make sense, or if you want some clarification or anything like that, right? So please, if you're there in chat, you can let me know partway through if at any point something stops making sense, right? But what I've seen when you've done these ones, for the rotations, you seem to be getting those down pat with the arcs, right? Because what we do for the arc, like I mentioned, is we take the point, this guy here, the pointy bit, that one goes on the center of rotation. And here we're told the center of rotation is the origin, right? And the origin is 0, 0, right here. So, I'm going to need, I hope my camera, oh boy, my boom cam is, my DIY boom cam doesn't like being moved like that very frequently. But anyway, so I've got it zoomed in a bit here now. Maybe you can see a little bit better, right? This point is going to go on the origin, which is right here. And then the lead point is going to go on one of the points of the shape, like so. Now, it can be useful to sort of push it so that it's a bit more closer to horizontal, like what I've got here. Either way, Once you've got it arranged like this, right, with the lead on the point of your shape and the pointy bit on the center of rotation, now you're going to draw an arc. And keep going even if you go off the grid here, because this grid is obviously only a small partial grid. So I'm going to keep going, keep rotating, keep rotating. There we go. And make sure that you go past 180 degrees. So we know 180 degrees is a straight line opposite. So now I've made sure to go on past that straight line. Now what I'm going to do, remember our next step is to draw a line from the point that we're rotating to the point of rotation, which in this case is going to be the origin. So we draw our line like this, right? So this is our step 2. Right? Actually, I'll tell you what. For this one, I'm going to do it in ink because I want color-coded so I can show you afterwards which part is which. Right? So drawing this line here is step 2. So step 2 was that one in red. Step 1, and this corresponds to the steps, Esther, that I sent you earlier in the email, and I sent you another day. So I'm going to do these in different colors here now so that what I'm doing clearly corresponds to the different steps that I've told you about. Step 3, I'm going to do in blue. Step 3 is to draw an angle. But now, if at this point, right, this is where we can rotate it by any degree that we want. You see, I had to line it up sort of like this, right? So this is my protractor here, and this protractor is now lined up once the overexposure gets out of the way. There we go. This looks better. So now we see that it's lined up here on the origin, and now I can draw my angle in whatever direction I want. Now this one happens to be 180 degrees, so 180 degrees is easy, right? Because 180 degrees is a straight line. So I'll just put a notch over here at 180. But you can see how now that I have my protractor here, at this point, I could rotate it by any degree that I wanted. If I was supposed to rotate it by 100 degrees, I would go to the 100 here, right? Because it's the inside one I'm using now for these numbers, and I would put a notch here. If I was going to rotate it, 140 degrees, I'd put one up here at the 140, right? So at this point, I could rotate it by any degree that I wanted to, but I'm doing 180 because that's what I'm told to do. So now I'm going to take my blue line and continue it across like so, right? So I know it looks a bit silly that this part of the line is red and this part is blue, but that's only because in this case we're doing 180 degrees. When we do this other one down to number 6, you'll see that the angle will change between the red and the blue. And now, step 4, it's going to be in green here, and that's going to be to draw the new point at the point where the arc and the line intersect, which is right here. So this now, this green X, that is going to be our new point. And that's just one point on the shape, right? Please don't be tempted to skip ahead now and to just try to draw the entire shape with this being one of the points on it, right? Because it's more difficult to get it right if you do it that way. But you can get a preview of what it's going to look like by taking it and turning your whole sheet, right? I turned the whole sheet 180, and we see now that it's going to look like this once we're done. It's very easy, though, if you just try to draw it, try to eyeball it, or try to think, oh, well, this is where one point is going to go, so I know what the shape is going to look like. The shape has to be oriented like this. And you have to know that once it rotates 180 degrees, it's actually going to what was on the left before is going to be on the right. And what was on the right is going to be on the left. And what was on the top is going to be on the bottom. What was on the bottom is going to be on the top. The most wonderful thing about Tigers is I'm the only one. Break out into some AA Milne all of a sudden. Yes, that's good stuff. That's good stuff. That's a real... Well, I mean, it was British, right? But Winnie, the fact that he's called Winnie the Pooh is somewhat of a relation to Canada. Right? That was in our Heritage Minutes, boys. You seen this one? Winnie, after my hometown, Winnipeg. Right? Come along, Christopher Robin. You guys have seen these, right? The Canada Heritage Minutes? That's real stuff. That's real Canadiana right there. That's what this country is built out of. TV commercials talking about like inventing basketball and house hippos. The house hippo commercial, That's some real shit. Okay, so now I'm going to do it again. Step one, line a Reno, line it up. Like, right? You see? Lead on the point, metal part on the center. Lined up. Rotate it. Draw an arc. Oh. Keep the metal part where it is. Draw an arc. I know it's hard. It's hard to see what I'm doing. Hard to see what I'm doing here. Now, do not. Things not to do. Things not to do right now include do not draw your point at the combination of this arc and this line. You might be tempted to say, ah, great, I can save myself some work now. I can go ahead and just draw the point here because I've already got a line. A line's the same as a line, right? No, no, it's not. A line is not the same as any other line because the new line that I draw is going to be at a different angle because now we're not coming from this corner point. We're going to be coming from this point. Remember, you had to do all 4 steps for each of the 4 points you're rotating. I know, seems like a lot of work, but it's your second last math course. Your second last math unit even, last math course. Just do the work, and then it'll all be over by next week. So, drawing a new line from this point to the origin. Like so. You notice how it's a bit of a different angle than the previous one? That's because it's coming from here. Now I had to continue that guy out at 180. I will make a good show of it. I'll show you how we're actually going to do it, right? You know, line up the protractor and all that, even though it's a 180-degree angle, and I could just draw the straight line, like I've said, you know, a half dozen times. But now we're going to see that the line is going to be a bit of a different angle. A funny angle. It was behind you, Tyrone. When you back up, things come from behind you. I'm just gonna randomly break out into movie references too, like Snatch. That's a good one. That's a real good one. Okay, so there's another one. So now we see this is a point and this is a point. Like I said, I'm going to model good behavior, so I'm going to go and do literally all of them. All of them. Maybe I'll rotate some in a different direction so that maybe you can see it a little bit clearer. All right, so now I'm taking this bottom right point, gonna get my lead on it. I'm gonna rotate it. There's my arc. Keep drawing my arc. I'm gonna make sure that it goes, oh poop. All right. There we go. Put it back where it needs to be. I'm gonna make sure that I draw my arc far enough to get the 180-degree angle. Now, that one's a little bit off, but I mean these things happen, right? I'm not going to penalize you for having 1 or 2 points off as long as I'm seeing that all the steps are there and accounted for, right? We can't be skipping steps. Now I'm going to draw my line from the point to the center, like so, right? And you'll notice that all these lines are going to, of course, cross over each other, but they're all going to be at slightly different angles. And I'm going to go ahead and measure 180 degrees. Again, right, just doing the measuring to show modeling, you know, how we would actually do this if we kind of had to and had other shapes. Okay. Yeah. See, I do appear to be getting off a little bit, don't I? I am getting off a little bit. Maybe yeah, my blocks are accurate. I guess I'm yeah, it's actually quite easy. It is quite easy to end up yeah, there we go. That's more like what the arc should be. Yeah. See what I mean? I mean, I can understand that these are some frustrating questions sometimes because it is very easy to have your arcs be off a little bit. Because look, right? You see there the difference between these 2 arcs that I just drew. At the start, these both looked the same to me, right? And we can see that over the course of drawing the full 180-degree arc, this one here ended up out a lot further. This one here was in a lot further, right? And this one here actually gets us to the right point. The point that we are supposed to have is this one here, which my second arc does get accurately. But my first one didn't. And that is an example of the fact that, you know, rotations are a difficult one, for sure. And I'm not going to penalize you for having the arc, extend out or in a little bit. I know some of the shapes are going to be off, but I do need to see all this stuff going on so I can see, okay, well, she's making a good faith attempt at doing the method that we're teaching, right? And then just one more point. I mean, you might not need to rotate the last one, right? Because you can probably just draw the last one based on the others, but whatever. I'm going to keep going because I desperately need to waste time out of my day. That's not true. All right, there we go. Draw my arc like so. That's my inside one. Now to do it again. Corner to the midpoint. Draw the angle. It's 180 degrees, so it's going to be over here. Draw the line like so. We see it crosses right there. And it is very hard, as you're seeing. It's hard to keep track of sometimes at this point. But now we have the shape. That one there. This one here. This one here. This one here. Color it in. And there we go. That is our shape rotated 180 degrees about the origin. Now like I said, I am going to go ahead and do question 6 as well. Okay, so question 6, this one down here, we're going to be rotating 90 degrees counterclockwise about the origin. And let me zoom in a little and give us a bit of an angle so you can see my hand, the way it's going to be moving around there in order to get these. There we go. Not bad. Not a bad camera position. Okay, so again, right, step one, we're going to be doing on the point here, on the point over there. Now this is a triangle, so we're going to have a little bit less to do. 90 degrees counterclockwise is 90 degrees to the left. So now I'm going to take my arc, my compass, and I'm going to draw my arc like so. And I'm going to try as hard as I can to keep the metal point constant while moving the lead. That can be tricky, but that's what I'm going to do here, right? So that was step 1. So again, right in pencil, the pencil bit is step 1. Step 2, I'm going to do in red again. All right, so this one is about the origin. So I'm going to draw a line from the point I'm rotating to the origin, like so. Now you're going to see the difference in the step 3, right? Because now my step 3 is going to be 90 degrees counterclockwise. And like I said, counterclockwise is to the left. So 90 degrees to the left, what's that going to look like? Well, it's going to be in this direction, right? Because it's to the left. And I'm going to put the crosshair, sort of the middle of my protractor, on the origin. Line up this leg on the bottom, right? Line this line on the bottom of the protractor with the leg of the angle. Then I'm going to make a mark over here at 90. So here it is, 90 degrees. Put a notch there. Then I'm going to draw my blue line. Just making sure I'm getting this lined up correctly. Draw it out like so. And now we'll see that 90 degrees counterclockwise. Well, the point, our first point, is going to be this one here. Step 4. Right? Now, again, if we want a preview of what our shape is going to look like, we can even just take it, right? Take our paper and rotate it 90 degrees counterclockwise, and we can see what it's going to look like, right? And from this, we could now easily go ahead and do our shortcut method, right? But like I told you, sometimes, like on your test, you're going to be doing 45-degree rotations or 135 or something like that, right? So you're not necessarily going to be able to just use the shortcut. Now, if you use the shortcut method, like I mentioned before, I am okay with that, but you do need to be able to write out sort of the workings of like the x to the y sort of thing, like the rotation rule your book calls it. But I say my basic philosophy for teaching sort of math like this is to show students the way that works every time, even if it's a bit longer, because learning one method is easier, but also then the confidence that you get from knowing that, hey, no matter what, this is the way that I'm going to be able to solve this question. Even if it takes a bit longer, I think students appreciate that, and it helps people to understand what they're doing. Right afterwards, once they learn that method, if they want to go on and do shortcut methods afterwards, that's totally fine. That's one reason why I think that, say, the way that quadratic factoring is taught in this program is a little bit backwards, because it teaches all the shortcut methods and all the edge cases, like, the difference of two squares and stuff like that. It teaches that first, and then after they're like, oh, by the way, you could use this quadratic equation, and that'll work every time, but why bother? It just takes a long time. In my mind, you start the other way around. You show them the one that always works, even if it's longer, and then afterwards, show them the shortcuts that they can use once they understand a method that's going to work every single time. But anyway, it's just sort of a pedagogical difference, but I do think that it makes a big difference, especially for building confidence in people that maybe struggle a bit with math, right? Showing them a way that's always going to work, even if it takes a bit more effort to do, oftentimes helps build some confidence and gets people, more on board with doing the math that you're asking them to do. But anyway, so there's an arc for this corner point, like so. Right then into the center, like so. There's my step 2. From that point, my step 3 is going to be using my protractor and drawing a 90, which I am going to do like so. Then I'm going to join those up with my blue line, thusly. And now we see that our point is going to be about out here. Again, right, I am a little bit off on these ones, just because it is quite difficult, especially even just kind of like the thickness of your pencil, the thickness of your line, even just the thickness of this mark. Like, I mean, you look at, because I blew this up so much, I mean, this coordinate grid, I mean, that's a solid like 2 millimeters thick, that line there, right? So, I mean, depending on what part of the line I put my compass on, even, you can have your rotation off a small bit. Now, again, right, with an arc, and then a more different arc. So here's the arc from this point. I know where it's supposed to hit. And there we go. So I draw that arc, like so. Try to get it a bit dark enough so that you'll be able to see it once I scan it and send it to you. Right, red line next, from the point to the origin, like so. Blue line then, from the origin back out at 90 degrees. Like so. I'm sort of crammed up into the corner of my shot here. Hope you're enjoying seeing my sideburns. There we go. Put the next there, and there we have it. Those are our 3 points, so I'm just going to take them and join them up. 3 is much better. Honestly, like, all these rotation problems should be triangles instead of other shapes, because boy, it takes a while. It takes a while if you're going to model good behavior and actually rotate every single point like so. And there we have it. There we have it. That is our rotated shape, 90 degrees counterclockwise about the origin. Let me now zoom. Zoom. There we go. It's pretty good. Okay, Esther, I hope that was helpful for those topics, right? Like I said, you are, I do think that you're going to be totally ready to go do the test on Thursday, right? There's no reason to sort of beat yourself up over not getting all of it, right? But also, I do think that these ones are Totally approachable, just they're a bit painstaking. Like it takes a while to do them, as you saw here, right? I mean, like it took what, like 2 or 3 minutes to do those ones, and then a solid like 10 minutes each for these, right? So these rotation ones do take a bit more work and time than the other reflections and translations ones, right? But it's mostly about just being just taking the time to follow through all the individual steps and not being tempted to take shortcuts, because generally with these questions, most of the shortcuts end up being wrong, right? Like drawing multiple points on the same line or something like that. But that's not to say that you can't, because like we saw down here, right, when we took our shape and rotated it, right, we had a good preview of what the shape was going to be, and it turns out that, hey, it did match. It did match our rotation, right? And up here, say if we took our original one again, right, and rotated that 180, we say, hey, look, that shape does match up with the shape that we found when we drew it like that, right? So there are ways, even on a test or something like that, to check and make sure that something like a rotation is working correctly. Okay, I'm gonna pop back over to my intro screen here. Let's go back to taking a look down at the gut again. Right, the gut filled up with our 7 square meals a day. Oh, stream starting soon. Hold the phone. Hold the phone. No, it's not. It ain't. It is already going. There we go. Okay, so that was geometric transformations again. Hope that was useful. Next up, I'm gonna do some radical stuff. Betty Ann, if you were in chat there, let me know, and I can do some other questions if you need. But I will just do the ones I've got written out to do are numbers 5 and 6 from, let's see, from this assignment. Yes, I'm actually going to do 6 then 5 because strangely enough, I think this assignment is a little bit backwards as far as like the difficulty of the sections go. Because question 6 is relatively straightforward, and you did a really good job at these ones. Just I want to show you what it means to then check for extraneous roots, right? But it's actually, oh, I'll flip that one over. That has some residue from the graphing on there. It's actually fairly straightforward, but it is something that you still have to fill in when you're doing it, right? So this is math 2101B unit 1. Zoom out a little here. Try to get my paper lined up a bit better. So 6a, solve the equation for root 3x equals 9. Okay, let me, there we go. Let me change my background. It's a different section, different background. Root 3x equals 9. Well, that's not hard, right? So that means we square both sides and we get 3x equals 81, right? Then x equals 81 over 3, or x equals 27, right? So that's pretty straightforward, right? And you got all these ones right. All you had to do then to check for extraneous roots, all we need to do that is just take this and put it back in. I know it seems a bit silly, right? But that's all we're doing. Root of 3 times 27 equals 9. So I'm just taking x equals 27 and putting it back in up there. Root 81 equals 9. 9 equals 9. Check. We got there. Did it. That's it. That's all you had to do to check for extraneous roots. It's one reason why it's not worth a whole ton of marks to check for extraneous roots, but you know, it is still a part of the question. Right? So this is the cube root of 5x minus 7 equals 2. Now for roots like this, right, like cube roots and stuff, it is important to make sure that you're getting the number sort of in the hook, sort of in this part. Either that or use the fractional root. I do prefer fractional roots myself in general, but symbolic roots like these are totally fine too, right? But then the cube root of 5x minus 7 equals 2, so we just cube both sides, right? So 5x minus 7 equals 8. 5x equals 15, x equals 3. So now all we've got to do to check again is to take this and put it back in up here. So the cubed root of 5 times 3 minus 7 equals 2. Cube root of 15 minus 7 equals 2. Cube root of 8 equals 2. 2 equals 2. Checks. Works out. That's it. Question C. I might not do all these, seeing this is fairly straightforward. But you know what? I got a few minutes. Maybe I'll carry on with these. 5x minus 1 minus 4 equals negative 1. So root of 5x minus 1 equals positive 3. 5x minus 1 equals 9. 5x equals 10. X equals 2. Easy peasy. All right, but then root of 5 times 2 minus 1 minus 4 equals negative 1. Right, so now I'm just going to go ahead and evaluate and see if that is actually true. Root of 10 minus 1 minus 4 equals minus 1. Root 9 is negative 1. 3 minus 4 equals negative 1. Negative 1 equals negative 1. Yes, indeed. Yes, indeed it does. Negative 1 does indeed equal negative 1. So that's all that we've got to do for checking for extraneous roots. Let's go back and plug those ones in. Right? Just a simple sort of additional part to those questions. Now there is, boy, the angle of my camera is off because my page is not appearing very square. Right? You know that you're on an angle when the bottom side down here is wider than the top side up here, and that's because the camera is sort of at an angle that I don't want it at. Anyway, there's no reason not to want it at that angle. Just my just my own sort of anal retentive sort of OCD nature about anything that I'm making. It's got to be all the little details. It's got to be right. Very detail oriented is the positive way to spin. Worried about the small stuff. Anyway, math 2101B unit 1, and see now I'm zoomed in too far. All right, whatever. So like I said, I want to do question 5 on here. Question 5 has a bit more substance to it. Okay, so suppose the function that, where s represents speed in meters per second, and l is a leg length of a person in meters, can approximate the maximum speed that a person can run. Okay, so if this was a real formula, then we would kind of be dealing with physics here. I mean, I imagine this is a made-up formula. I don't know. Has anyone in chat done kinesiology? Can you tell me if this is actually the formula to relate someone's speed to their leg length? I got my doubts, but maybe. I mean, I don't know. I never did kinesiology. So this is question 5. So S is equal to pi times the root of 9.8L divided by 7. Right? Boy, oh boy. So what is the leg length of a person with a running speed of 2.7 meters per second? Okay, so I assume that, yes, the speed here would be in meters per second, judging by the units that we have. So all I'm going to do, well, we know that S is equal to 2.7, so I'm going to fill in 2.7 over here for S. It's going to be 2.7 equals pi times the root of 9.8L over 7. So I'm going to have to solve for L, which means I'm going to need to get the L out of this square root. So the easiest thing to do is going to be to divide both sides by pi. So one of the sides of my equation is just a full radical. Then I'm going to go ahead and I'm going to square both sides, right? So on top I'm going to have 2.7 squared Below I'm going to have pi squared, and over here I'm going to have 9.8 L over 7. Right? Now I could, of course, evaluate this 2.7 squared over pi squared. I'm just going to keep going. I'm going to do all the rearranging first, then I'm going to do the number crunching afterwards. So I'm going to have 2.7 squared over pi squared. I'm going to multiply now. I'm multiplying both sides by 7 over 9.8, right? So that's just the way we're going to get rid of this fraction, right? Times 7 over 9.8, like so. And we're going to see, of course, on this side, this cancels, this cancels, this cancels, obviously. So then we're left with just sort of this mess over here. But now we're going to have to go and figure out, well, what is that answer, right? So I'm going to break out my good pal, my mathematical Game Boy over here, my TI-84, boot her up. I hear that that Linus Tech Tips did a liquid-cooled TI-84. That's is that a real thing or is that just a meme? Either way, I am on board. Right. So on top we're going to have I'm just going to write it out like this: 51.03 over. So I'm going to do pi squared. I'm going to use the pi button on my calculator. Now, if you use 3.14, you're going to get a nicer, shorter decimal than that, times 9.8. I'm going to round that to say 2 decimal places as well. So I'll call that 96.72 equals L. And I'm just going to divide them. 51.03 divided by the answer to the last question. It's going to be 0.52. I'll call it 0.5276. Right? And they asked for the nearest tenth of a meter. So we could just say a person. Now, a tenth of a meter, of course, is just this first one here, right? So a person with a running speed of 2.7 meters per second, but have a leg length of half a meter. Seems to me that, more than your leg length is involved in figuring out how fast you can run, but what do I know? I'm not a sprinter either. All right. So, Betty Ann, those are a few questions for the unit that you were currently working on. Like I said, you can always let me know if you have any other questions, and I will get to those. But for now, then, I am going to switch back over to my intro screen for a second. And I'm going to talk about permutations, sort of the definition of permutations, and then the NPR formula. That is not National Public Radio, although I do very much enjoy NPR. If you want to see some really good NPR content, look up their. They have these interview series with classic characters where they interview like classic American characters, but like not the people who play them. They interview the actual character, and they do one where they interview Cookie Monster from Sesame Street. It's amazing. It is fantastic. It's one of the best like 5 minutes of YouTube video, like radio stuff that I've ever seen. It's incredible, and it's not just a radio; it's a video too. So it's actually like the Muppet Cookie Monster there with all the puppeteering stuff going on and the actual voice actor. It's incredible. So they ask Cookie Monster what his favorite word is. Out of cookie. All one word, just out of cookie. It's good. Ask him what his favorite word is. He's like, "What? You serious? Cookie." My Cookie Monster impression is, it's like 6 out of 10, 5 maybe. It's not great. I only have a few impressions. Right, my Ray Romano is okay. No, Deborah, no. It's pretty much just those words though. No, Deborah, no. I'll stop. Boy, oh boy, I'm gonna lose whatever viewers I had. The more Uh, it just goes off the rails. He's not even really talking about math. He's just Cookie Monster and Ray Romano, and then does like a Jim Gaffigan voice. I don't understand. Okay, so Calais, I'm going to link you to this point in the video and not that previous part. So hello, hello, future Calais. This is past Peter, talking about permutations and combinations. So permutations and combinations are some of the ways that we are going to use some of the factorial math that we were just looking at, right? They're both very practical, very useful statistical operations that we see quite a lot in sort of probability and other sort of stats modeling. But over here, this is from page, let me see. This is page 92 in your textbook. We see down here in the corner. This is a really useful page. You might be flipping back to this one a lot. Um, it has a very good summary of the stuff that you've covered in the course so far. So when you're working on your assignments and stuff like this page might be a dog-eared one to turn back to, right? Or I guess you're using a digital textbook, aren't you? Well, virtual dog-earing. So the number of permutations from a set of n different objects, where r of them are used in each arrangement, can be calculated using the formula this. Right? Remember how I talked the other day about the number of different orders of a set of playing cards, right? And excuse the noise on stream here now. I'm opening up a new set of cards. I'm going to use my, hey, remember this guy? I did show and tell about this guy. Or this little guy? Yeah, that's my Greek knife. That's my 10-euro Greek knife that I use constantly. And it's currently opening up a new pack of playing cards. Hold on. Come on. There we go. There we go. I'd get there eventually. Okay, so here's the cards. Get rid of the jokers. New set of playing cards, right? And I talked before about how the different orders of these playing cards, all the vast number of orders that you can make of these cards, are represented by 52 factorial. Because that's what factorial does, is it tells us the number of orders of sort of a set of objects. And would you look at that? Look, they're already marked. I haven't even opened them. That is garbage. Teach me to buy packs of cards at Dollarama. Look at that. Right? Look at see the darkness on the back of that? That is a marked card. Well, it's a useless deck, but I can still use it for class, I suppose. I can use it for illustrations. But if we had, if we have just 5 cards, even, just 5 cards, there's loads of different ways that we can put the order of these 5 cards, right? And it's 5 factorial that we would use to find that out. And we know that from doing 5 factorial, there's 120 different ways to organize all these cards, right? Like if we did 2 factorial, these two, there's 2 different ways, right? We can either have 8, 7, or we can have 7, 8. That's it. As soon as we bring another number into play, all of a sudden now there's 6 orders. There's this order, which is 1. This order is 2, right? So there's 2 different orders with 9 on the front. With 7 on the front, there's this order, 3. This order, 4. With 8 on the front, there's this order, number 5. And this order, number 6. Right? So we see that basically a factorial tells us how many different orders there are of a set of objects. Right? Now, permutations and combinations are able to go a bit beyond that. They can tell us a bit more stuff, right? So a number of permutations. So All right. So a permutation formula, NPR, like that, lets us pick a subset of objects out of a larger set, then determine the number of possible arrangements. Right. So we know that if we have, say, 5 like that, right, then our number of 5 factorial, our number is going to be 120. So there are 120 different orders of 5 cards in or of 5 anything. Now, how many different ways? Say I was to randomly pick 2 of this 5. How many different orders of those 2 could I get? Well, I could have 8, 7, but I could also have 7, 8, right? And those are 2 different ones. Well, I can also have, 9, 8 and 8, 9. I can have 9, 7 and 7, 9. I can have Jack, 10 and 10, Jack, right? There's lots of different ways to pick 2 out of those. But that's what I'm doing if I do, say, NPR, or if I do kind of the way I like to read it is pick, right? So NPR sort of, say if it's 5P2, then we're looking at, like, say, 5 objects, and we're going to pick 2 of them. And how many different ways are we able to pick 2 objects out of a set of 5, right? Well, we know that NPR, our formula, like it shows here on this page, is going to be n factorial over n minus r factorial, right? And now this is where order does matter here. This is not important right now, but it will be important as soon as you get to your next unit. That when you're doing NPR, order matters. When you're doing NCR, which you're going to see in your very next unit, then the order doesn't matter, right? So actually my playing cards illustration is not as good for NPR as it is for NCR, because say 52C5 or 52 cards and then choose 5 of them, that is literally the number of total 5-card hands that there are out of an entire deck of playing cards, is 52C5. It's not 52P5 because the order that you're dealt the cards in doesn't actually matter. But anyway, I'm getting a little bit ahead of myself here, but it is kind of something that I like to teach at the same time. But anyway, so NPR tells us, say 5P2, if we have 5 objects, how many ways can we pick 2 objects out of that set of 5? Right? So here's our 5 objects. How many ways can we pick 2 of those? Well, what it's going to be is 5 factorial over 5 minus 2 factorial. So that's going to be 5 factorial over 3 factorial, right? Which is just going to break down into 5 times 4, which is, of course, 20. So what it's telling us is there's going to be 20 ways to pick 2 things out of this set of 5. Okay. When all n objects are used in each arrangement, n is equal to r, and the number of arrangements is just equal to n factorial. Yes. Right? So that's important. It is also important here to know this, that 0 factorial is equal to 1. Right? By definition, 0 factorial is equal to 1. So that is super important to know. And it is, like it says here, it's literally just by the definition of what 0 factorial is. I realize that you can't take the factorial of a negative. We've talked about this. And it seems like the factorial of 0 should just be 0. But in order for certain types of math to work, we had to define 0 factorial as 1. So it is important to remember that. But I know that the explanation that I have just given might seem a little bit confusing, right? So what I'm going to do now, aside from moving some stuff around, is I'm going to go do a few questions on this topic, and I think that will probably help to illuminate what I'm saying a bit better than just talking about the theory behind it. Although I do think the theory is important still. So let me zoom in here. All right, so I'm going to do now, this is page 104. I'm going to do questions 1, 2, and 3 here. Question one. Question one is fairly straightforward, but I'm still going to walk you through these ones just really quickly. 7 factorial over 3 factorial times 2 factorial. Well, that's going to be the same as 7 times 6 times 5 times 4 times 3 times 2, right? Divided by 3 times 2 times 2. I'm going to start leaving out the times 1s because they don't do anything, of course. We can say this 2 can cancel with this 2, and this makes a 6, and that cancels with that 6. So we're left with 7 times 5 times 4 times 3, which is 35 times 12, which is 350 plus 70, which is 420. Hey, LeMayo, look at that. 7 times 5 times 4 times 3, 420. Nice. All right. Hey, LeMayo, huh? There we go. What you say when you see your good friend LeMayo. Hey, LeMayo. How many different signals? Oh, sorry. No, let me do a few more of question one. Let me do a few more question one before we're done. 1b, 8 factorial over 2 factorial 2 factorial 2 factorial is just going to be 8 times 7 times 6 times 5 times 4 times 3 times 2. Divide by 2 times 2 times 2. And I happen to know that 2 times 2 times 2 is the same as 8. So that's just going to be the same as 7 factorial, which is, I'm going to do it on my calculator so as to not go through and multiply all those out. There we go. $50.40, like so. Let's do let's do C and then move on. C is 10 factorial over, my God, 4 factorial, 3 factorial, 2 factorial. I don't know why. Like my brain just blanks for a second. I'm like, draw. My brain is like, you should draw 4. My hand is like, oh, what? You mean a 3? 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 over 4 times 3 times 2 times 3 times 2 times 2. Okay. So I'm just going to start canceling. 4 times 3 times 2, 4 times 3 times 2. 3 times 2 is 6. Get that out of there. Then I'll cancel this 2 into the 10 and make it a 5. So what I'm left with is 5 times 9 times 8 times 7 times 5. And that's going to be 12,600. Okay, so that's fairly straightforward. But that's not really the material that you came or that you asked me to do, right? So I just wanted to do that just as a reminder, a bit of a refresher in how we cancel the factorials. But now I'm going to get into some that actually use sort of NPR. So how many different signals can be made from 6 flags hung in a vertical line using 2 identical white flags, 2 identical red flags, and 2 identical blue flags? Okay. Oh, I'm actually a little bit wrong, actually. These aren't going to use NPR right now. So question 2. So we have 6 flags in total, right? So we have 6 on top, like so. But then we have 3 that are identical, 3 sets, right? So we notice that we have 2 red that are the same, 2 white that are the same, and 2 blue that are the same, like that. Right? So what I'm going to do now is those down below. Why that? Well, because what we have to divide by is number factorials for each of the ones that are the same, right? So we have 2 identical red, so I put a 2 factorial down here. I have 2 identical white, and I have 2 identical blue, like so. So the order is going to be 6 times 5 times 4 times 3 times 2. Divide by 2 times 2 times 2. This 2 is going to cancel there. This 4 is going to cancel with those 2. We're going to be left with 6 times 5 times 3, which is 30 times 3, which is 90. So we see from question 2 on page 104 then, we're going to end up with 90 different orders for those. So 6 nickels are flipped simultaneously. How many ways can 3 coins land as heads and 3 coins land as tails? Um, hmm. Tell you what. Tell you what. I appear to be now. These aren't actually the questions that I wanted to do today. Actually, I'll tell you what. Um, let me. Sorry about this, but I am going to check back over to your. Let me look at your study guide here. Uh, you asked for section. That's for section 2.3, I believe. Yes, pages 93 to 94. Okay. Okay, that was the wrong page. Apologies. Apologies. Pages 93 to 94 you asked for. Yes. Okay, so I realize now that I start doing these questions is that I am getting ahead of what it was that you were asking. Here we go. These are the ones. Apologies. Apologies, Kelly. Um, I had picked the wrong page to start off with. Okay, here we go. Yes. All right. Put a pin in these. We will get to these. Sorry, it's a little bit haphazard here now, but yeah, you will have to do those eventually. This is Math 2101B, right? No, sorry, 3101A. My goodness, 3101A, Unit 2. Okay, and this is now page. This is the correct page. Yes, page 93. Okay. So let's do a few of these first ones here really quick. All right, so 1A. Well, we know that NPR is just n factorial over n minus r factorial, right? So with this in mind, we're, excuse me, equipped to handle these questions. So then 5p2 is going to equal, I literally just did that one. I did that one just off the top of my head. I maybe that's what it is, right? I'm prophetic. I actually knew in the back of my mind, I knew what the question was going to get onto, right? Which equals 5 factorial over 3 factorial, which equals 5 times 4, which equals 20. Easy peasy, sorted. So 1B. Do they throw any real curveballs in there? Oh, E is a bit of a curveball. E and D are curveballs, right? So I'll do a few of these. I do want to show you some of the curveball questions because there's always some of those. 8p6 is just going to be 8 factorial over 8 minus 6 factorial, which is 8 factorial over 2 factorial, which is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 over 2, which is just going to be, I'm just going to do 8 factorial and divided by 2, because that's going to save me a little bit of number crunching. 8 factorial is that. Divide that guy by 2. There we go, 20,160. So A, B, I'll do C, D, and E, I suppose. 10p5, you're noticing this is getting a little bit quicker, right? 10 factorial over 10 minus 5 factorial, which is equal to 10 factorial over 5 factorial, which is equal to 10 times 9 times 8 times 7 times 6, right? $30,240. Wasn't about to do that one in my head. Let's do question D. I do want to show D here. 9p0. What the heck? 9p0. What does that even mean? Right? And if you think a bit about what the definition of p is, then what the answer to 9p0 is going to be sort of makes a lot more sense. Because here what we're doing is we're saying how many ways can we pick 2 different objects out of a set of 5? How many ways can we pick 6 different objects out of a set of 8? How many ways can we pick pick 6 out of 8, pick 5 out of 10, but pick 0 out of 9? How many different ways can we pick 0? Well, how many indeed? Does this cause our sort of formula to short circuit and not work? No, it doesn't. It works just fine. There we go. There's one. There's only one way to choose 0, and that's to choose 0 of them, right? You just, you know. And by the same token, well, 7p7. And remember now, for p, the order does matter. Right? So that's 7 factorial over 0 factorial. So here now this calls back to what we were looking at just at the start, right? How 0 factorial equals 1. It's super important. That's a rule you have to memorize. 0 factorial equals 1. So this now is just 7 factorial, which is, well, we did that on the previous page, but I'm going to go ahead and do it again here now. 7 factorial, 5040. 5,040 different ways. And seeing I've gone this far, we might as well do f as well. F is 15p5. So that's 15 factorial over 15 minus 5 factorial, which is 15 factorial over 10 factorial, which is 15 times 14 times 13 times 12 times 11, which is going to be what? 15 times 14 times 13 times 12 times 11. Oh, ha! I did not mean to have that log in there. I'm gonna be honest. That was a fat finger. Right? That's how you end up like innervating a tank, right? You fat finger. I mean, I guess you really shouldn't have innervate keyed in the first place because it's such an important cooldown. But you know, I mean, at times you want to grab that one quick, right? I mean, you're not always in Blackwing Lair or something lackadaisical. Sometimes you're in player versus player, and you gotta respond fast. Anyway, exactly nobody understood what that sentence meant. I'm sorry. I fat fingered that log, but anyway, I had to go. I knew a decimal answer was not what I was going to get, so that was a sign. I had to go back and evaluate and get that. Right? So, but this is not the only type of question that you would want me to do for these ones, I am sure. So I'm going to do a few of the other ones that sort of indicate what these topics mean and how we can go about using them. For example, let's look at questions. Let's look at questions 8 and 9 over here on the side. So in question 8, then, we see a wheelchair basketball team sold 5,000 tickets in a draw to raise money. How many ways can the tickets be drawn to award the first, second, and third prizes if each winning ticket drawn is not put back in prior to the next draw? Right? So there's a lot of different ways that we can model these sort of questions. And for units like this, it is important to sort of think about what we're doing, right? Now we understand that there's 5,000 people to win the first ticket. Then because the person is not put back in, there's 4,999 for the second ticket, and there's 4,998 obviously for the third ticket. So what we could do is we could go straight ahead and do, well, we know it's going to be 5,000 times 4,999 times 4,998. And we know that that is going to give us the answer that we're looking for. However, the point of this unit is to understand how we're going to do NPR and NCR, right? Or sort of just NPR for right now. So what we're doing here now is there's 5,000 people who could win, and we're picking 3 of them, right? So it's actually 5,000 P3. So what we're doing is 5,000 P3, right? And in a small case like this, where we've got 3 numbers, it does make sense to sort of think about it and to write it down. But we are actually doing this, right? And if we work through it, we'll see how this makes sense. Because on the top, we have 5,000 factorial. And then below, we have 5,000 minus 3 factorial, right? Which is 5,000 factorial over 4,997 factorial, right? Which is the same as 5,000 times 4,999 times 4,998 times 4,997 factorial. Hey, I got there. I got it in. I got it in right on the side. And then down below, it's 4,997 factorial again. These two are going to cancel, and we're going to be left with, just like what I had over here, just like what I knew we were going to need before I started, 5,000 times 4,999 times 4,998, which is going to be all right. This is another good this is a good example here, right? Because it's showing us what in the world is this? This E11. Well, this is scientific notation. And again, you're going to get tired of me saying this before your program is done. But this is a topic that they're going to have expected you to have already learned before you did this. But what this means is it's a 1 point, I'll call that 1.25. And E here, E is the same as times 10 to the 11. And then the 11 is what goes up there in the corner. So this is what we call scientific notation. But this is just a way of writing out a really big number. What it means is you would have to move this decimal place 11 places to the right to get the actual number. But this is roughly how it would be written. So how many ways can the tickets be drawn to award the first, second, and third prizes if each winning ticket is not put back in? 1.25 times 10 to the 11. It's quite a few. That's the answer for this one. Right? Let's do question 9 as well. I'll do question 9 and then I'll call it there for the day. Kelly, if you have any specifics that you want me to go over, please do let me know. It's always useful to know the specific numbers of the questions, but I will endeavor to try to cover the topics that you mentioned in as much detail as I can. So if a Canadian social insurance number begins with the digit 6, it indicates that the number was registered in Manitoba, Saskatchewan, Alberta, Northwest Territories, or none of it. If it begins with a 7, number was registered in BC or the Yukon. How many different social insurance numbers can be registered in each of these groups of provinces and territories? Okay. Well, again, this is a bit of a different question. So they are sort of mashing together a few different ways of solving these all at once, right? But generally, we need to know that a social insurance number is 9 digits long. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 digits for a social insurance number, right? And we know that if it begins with a digit 6, indicates it was registered in Manitoba. So if we have a digit 6 up here, right, then these other ones can be any digit at all. How many different social insurance numbers can be registered in each of these groups of provinces and territories? But it has to be a 6 on the front here, right? But how many options are there? It's not 6 options, though, is it? It isn't, right? So it's going to be 1. So this is the number of options for each digit, right? And that's what we're filling in up here. So what are the number of options for the first digit? Well, it's just 1, right? Because it has to be a 6 if you're in Manitoba, Saskatchewan, Alberta, Northwest Territories, none of it. It has to be a 7 if you're in BC or the Yukon. So there's only one option for that one. Then there's going to be 10 options for this next one, right? Because 0 through to 9. There's going to be 10 options here, 10 here, 10 here, 10 here, 10 here, 10 here, and 10 here, right? So it's just going to be 10 times 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 10. So that is going to be, that's 8 tens. That's going to be a 1 with 8 zeros. Which is 100 million. Possible social insurance numbers in each group. Okay, so that example never actually used didn't actually use the NPR and NCR stuff that we're talking about. Okay, tell you what. I don't feel that I've gone over this in quite enough detail here yet. So I'm going to do one more question. I'm going to pick question 2 here. So this is going to be page. Right, this is still the same page. Oh, come on now. Still the same page, page 93. I'm going to do question 2. This is a really good question. I say that a lot. Create a list or use a tree diagram to count all the ways that a president and a vice president can be elected. Right? So let's go ahead and use a tree diagram, like it says there. So we have 4 people, Katrina, Jess, Nazir, and Mohammed, and they're running for student council. President and vice president can be selected. All right? So in my tree diagram, the way those are going to work is I'm going to start off with the president. Yeah. And then the vice president is going to be over here. So now there's, of course, 4 different options for the vice president, right? So we can have Katrina, we can have Jess, we can have Nazir, and we can have Muhammad, like so, right? So those are the 4 options, and generally we make it look like a tree by we kind of join all these guys up with different branches here coming off like so. And then the vice president, well, for Katrina, I know that Katrina can't be both president and vice president, right? Like we're not gonna mess around with having one person filling 2 roles. So after we pick K for the first one, we can either pick J, N, or M for the vice president over here, right? After we pick J, we can either pick Katrina, Nazir, or Muhammad. Nazir, we can pick Katrina, whatever J was, Jess, and Muhammad. And then for Muhammad, we can pick K, J, or N, like so. So now let me go through and draw out the next one. And you'll see that tree diagrams are a touch big, I understand. But it's a very, very, very thorough way of seeing all the different options in something like this. But I do want to show how to do this one, partly because, again, this is another topic that the book is going to assume that you have seen in your previous courses. Because I believe the grade 10, I think it is, covers tree diagrams in a fair amount of detail, whereas your grade 12 one does not, right? Because it sort of assumes that you're already used to doing out stuff like this. Now we have to list out what we call our sample space. Right? Now, listing out our sample space is super important. The sample space in a situation like this is all the possible results that we get. Now, sometimes for tree diagrams, we'll see sort of probabilities assigned to each tree. We're not going to go ahead and assign probabilities to these ones because it's equally likely, we're assuming, that each of these people get in. We're not assuming that, like, I don't know, Katrina and Muhammad are super popular and Jess and Nazir are really unpopular and they're going to have different probabilities. We're not going to deal with that. We're just going to assume that they're all equally likely. So the sample space, we have, basically we're just going to read across the paths, right? So the top path is KJ, then it's KN, then KM. We've got JK, JN, and JM. And we do know here that the order does matter, right? So for example, NM is not the same as MN. And the reason it's not is because the first letter represents the person who's the president. The second letter represents the person who's the vice president. So obviously, if the role the person is taking changes, then that's a different result, right? So that's why KJ and JK are both listed here, because the order does matter. So here now we've got all our sample space. These are every single result that we could possibly get. So create a list or use a tree diagram, and we have actually done both in the end, to count all the ways that a president and vice president can be elected. Well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 ways. Okay? So verify your results from part A using the formula for NPR. Good. This is why I wanted to get onto this one, by showing you that NPR could have got us to this 12 right out the gate, right? Without us having to do out all of this stuff, right? Because B, we have NPR. And remember, right? So we have 4 people choose, or I'll say pick. I like to use pick to mean, I know it's not pick, but pick 2 to be president and vice president, right? So we're going to do 4P2. Right, and there we have it. Right? I mean, I know this is a simple, this is a very simple example of the NPR formula, 4P2, but as you see, even something that's this simple in NPR, when we go over here to do it with a tree diagram or a list, it's actually rather labor intensive, right? So that's why as soon as we get up into like, I don't know, 50P4, 50P12, something like that, right? Doing it out this way would be a bonkers amount of work. But doing it out this way, practically the same as doing just 4P2. And even if you have a calculator like this, you can actually go ahead and use it. See, I've got those 2 formulas right here. Well, we haven't got onto NCR yet. That'll be the next time I'm talking about this stuff, I imagine. But I do have NPR right here that I can use. Now, not all calculators will have that. That is a stats function. Not so sometimes calculators will have stats stuff built into them. Your average scientific calculator doesn't. However, online calculators definitely will be able to. But either way, when you're writing it out by hand, like on your workings, on your assignment, and on your test and stuff, I do want to see this sort of action going on. So you don't need a statistical calculator to use this formula. All you need is a normal scientific calculator that has the factorial function in it, which they're going to. They are going to have the factorial. Okay, so then Calais, that was it was a touch rambling there for a bit. I sort of bounced around a little, but we got there in the end, right? Which may as well be my catchphrase. So yes, that was everything that I needed to get to today. Hope you were all entertained and engaged and not falling asleep. To reiterate what I said at the start, we are accepting applications to transfer at Academy Canada to Kenmount Road for the summer, but you will have to speak with Judy about that, and you have gotten that in emails already. If you have any specific questions about how that's going to go down, do please send them to me in an email. But as I'm saying, the stream here will be over as of the end of June, right? So we're going to go up to day 63. Day 63. Boy, it seems like just yesterday I was, looping my sound on day 2, which is a very good highlight that I didn't make, but it's available on my YouTube. It is available on my YouTube. Just click Reno down below on my profile, and you'll see a link to my YouTube, which does have some of those nice early videos that are delightfully raw, even more so than these ones. And that's saying something. Anyway, thanks for being here with me today. I hope you have a wonderful rest of your day. Stay safe out there, and I will see you again tomorrow for day 50.